Okay, so we're going to look at part C from question 1480 in your textbook. The following data were collected for the reaction between hydrogen and nitric oxide at 700 degrees C. So there's the balanced equation. These are the experimental data that we were given. In parts A and B, we found the order of the reaction as well as the value of the rate constant. So what we ended up with was that the rate of the reaction was equal to K times the concentration of the first reactant H2 to the first power times the concentration of nitric oxide to the second power. So that's the experimentally determined rate law in parts A and B. In part C, we're asked to suggest a plausible mechanism that's consistent with this rate law. And hint, assume that the oxygen atom is the intermediate. Now, one way I would change this question is to say assume that oxygen atom is an intermediate, because it turns out the mechanism I'm going to show you, that I will propose for you, suggests that oxygen atom is an intermediate, but not the only one. So let's move it up here a little bit. So the idea would be that a proposed mechanism involves elementary steps, and the sum of those elementary steps should give you the overall balanced equation. Furthermore, analysis of the mechanism of the elementary steps in their whole should be consistent with the experimentally determined rate law. This is what was determined experimentally. So here is one plausible or possible mechanism. It may or may not be correct, but it's one possibility. I'm going to propose that in step 1, what happens is the nitric oxide reacts with itself. One molecule of nitric oxide reacts with another one in what's called a fast or rapid equilibrium. There is a rate law, a rate constant for the forward reaction, so I'll write that as Kf, and there is a rate constant for the reverse reaction, which I'll write as Kr. The nitric oxide is in equilibrium with N2O2, dinitrogen dioxide. And what we can say about this particular reaction is that it is in fast equilibrium, which means that the rate of the forward reaction, this direction, is equal to the rate of the reverse reaction, this one right here. And so I'm going to write out, using these two elementary steps, the rate laws, and set them equal to each other. So for the forward reaction, we would get Kf times NO squared, and that would be equal to Kr, the rate constant for the reverse reaction, times N2O2. Okay? Now, we'll come back to that in a moment, but I'm going to propose that in the second step, there is a slow step, and this step is what we would call rate limiting or rate determining. And in this reaction, what happens is the N2O2, the intermediate from the first step, reacts with a hydrogen molecule, one of them. And a couple things happen. One is it falls apart, so you get an N2 molecule. Hydrogen picks up one of the oxygens to give you a water, and we're left with a second product, or third product I should say, which is the oxygen atom, atomic oxygen. That's back to that hint. Assume the oxygen atom is an intermediate. Now, the rate law for this one, which I'll call R2, would be K2, the rate constant for this reaction, times the concentration of N2O2, times the concentration of H2. Remember, for elementary steps, the rate law is equal to K times the concentrations of the reactants to whatever the coefficients are. In both cases, the coefficients here are 1, so these would be raised to the first power. Now, what happens after that? I'm going to propose a third step. This one will be fast, and in the third step, what happens is a hydrogen molecule, the second one in our reaction scheme, reaction mechanism, reacts with that oxygen intermediate to form H2O. I will write out the rate for this step, K3, rate constant is K3, times concentration of H2 concentration of O. Now, let's get to the point. When we write the overall rate law, it's going to be from the rate determining step, the rate limiting step, the slow step, the one that's the slowest. That limits how fast the products can be formed. That's right here. But it has an intermediate in it. So what we're going to do is we're going to get rid of that intermediate and write it in terms of reactants. The reactants in this reaction are H2 and NO. So the way we'll do that is I'm going to bring this right back down here, R2 equals K2 times N2O2 times H2. Okay. Now, coming back to the first step, N2O2 is right there. We can rearrange this equation in the first step to solve for it, to isolate N2O2. And if we do that, N2O2's concentration would be equal to Kf, that's the rate constant for the forward step, times the concentration of NO squared, divided by Kr. Very good. There we go. Now I'm going to substitute this back in to rate number 2, the rate determining step. Sorry if you didn't see that. N2O2 is Kf over Kr times NO squared. So now for rate step 2, it would be K2 times Kf over Kr times the concentration of NO squared times H2. Now here's the thing about rate constants. A constant times a constant divided by a constant, well, that's a constant. So I'm going to call that K prime. I'm just going to write that K2 times Kf over Kr. I'll just call it K prime. And so now we have K prime times NO squared times H2 for the rate determining step. And let's look at it. That's exactly what we saw as the experimentally determined rate law. A constant times H2 to the first power times NO to the second power. So this is consistent with that. This mechanism, three-step mechanism, is consistent with that. Remember, the overall rate law should really be determined by the slow step. And notice I had to tell us that that was the slow step. That's part of the proposal, is not only what's actually happening in terms of the reaction, but whether it's fast or slow. It's the slow one that's the key. So we now have, if we take all three equations and add them together, we'll get the overall equation for the reaction, which was given in the original problem. And this seems like a reasonable proposal, a plausible proposal. Is it the correct one? Remains to be seen. We would need to do more experiments, determine whether the oxygen atom actually exists during the reaction. We'd have to have some way of measuring the oxygen atom. Who knows? But in any case, this seems like a plausible mechanism. Generally, we don't expect people to develop their own mechanisms in an introductory general chemistry course on an exam, a three-step process anyways. We generally want to evaluate them if they're given. But this is the kind of thing that chemists do. They try to develop, based on their understanding of chemistry, what types of mechanisms might be taking place. And if they can determine that, it can help them to sort of develop methods for making a reaction more efficient, more effective, cost-effective, that sort of thing. So this is a nice little look at one possibility. Just one final point about this is that this mechanism, you can find this mechanism online. There's people have worked this out. You just Google it. Just write the equation into Google search and you'll find it. But there are other mechanisms for this reaction that have been proposed. One involves hydrogen peroxide. So again, it's not obvious which one is the correct one. We would have to study that.